Before we get into the meat of this chapter, I want to share with those who are looking at the video the documents that I would be handing out in class so that you can look for them in Brightspace. Of course, we've got the well, I can't even see myself now. Hold on a second. So I don't know if yeah, let's do it that way. Okay, so that's chapter 4 PowerPoints. Then we got next time we meet, we'll go into chapter 5. And there's the review document that I would hand out. And the worked problems look like that. And then I have a couple of extra credit projects. One is this periodic table. It has instructions on the front sheet. It has a blank periodic table on the second sheet that you fill in according to the instructions here. Print out a hard copy. I don't have a version that you can fill in like a PDF form. You have to print out the hard copy and do it by hand, and then either scan it or photograph it and resubmit it that way. But I want you to put your name up here. If you decide to do this extra credit, put your name up here and turn in both sheets, both the worksheet and the instruction sheet, because this has the points on it, and that's what I'll be using to grade it. And then I have this second project. It's called 50 Ways to Name Your Compound. Instructions are in here. You'll have a list of 50 either compound names or compound formulas. And if you have a formula, then in the answer sheet, you'll put in the name. And if it's a name, you put in a formula. And this is to give you practice naming compounds. And beware, I can tell on some of these compounds whether or not you actually learned how to name them or you just looked them up on the internet because of the spelling. I won't be able to catch all of them, but if you just look them up on the internet and fill them in just to get extra credit, then you're not doing yourself any good. You're just getting points, and that's not the objective of these extra credits. Okay. Let's see, chapter 4. Let's turn this into a slideshow. Here we go. Chapter 4, we're going to do chapter 4 and chapter 5 are exam 2. So we'll get to chapter 5 next Thursday, probably. Chemical foundations. All right. Now we're going to get, in chemical foundations, we're going to get into the meat of chemistry. We're going to start at the atomic level. And for chapters 4 and 5, you're going to have to know your chemical symbols because we're going to use them. That's your alphabet. That's the chemistry alphabet, is the symbols for the elements. Then we're going to build words with them. We're going to build compounds using those symbols and the rules that I'll give you. And then, not in chapter 5, I think maybe, yeah. Not for this exam, but later we'll build sentences with these words, these compounds and their names. We'll build sentences, which is chemical reactions. Okay, and learn how to use them to answer questions, right? Deeper questions than just regurgitating facts. All right, so for chapter 4, this is just a general outline, and I put it in there just so we know the topics that we're going to cover. All right. When I first put this slide together, there were only 115 known elements. Now there are 118. In fact, all 118 elements in the periodic table have names. There was a time when we had placeholders stuck in there because either we hadn't discovered the elements or the elements had been discovered but not named yet. But there are 118 of them, and about 88 of them are found in nature. Some sources go as high as 98. And the reason for that is that elements that were created in the laboratory in the past now can be discovered in nature, not from contamination, but they are naturally occurring elements. And the reason we can find them now is our analytical techniques are more refined. We can detect smaller amounts. So those that were at one time man-made, 10 or so of them now are identified as naturally occurring. Just like our alphabet has 26 letters in it, the English alphabet has 26 letters in it. The chemical alphabet has 118 letters. And I've only asked you to memorize about 60 of them because they're the most common. They're the ones that we're going to be used. Okay. Yeah, go ahead.
I couldn't find the quiz. Where is it as on Brightspace?
Um, Hold on a second. Let me, we'll come back to this. Let me stop the share and go into the, let's see, not there, here, I think. Share my browser. Okay. Let me go into the course, right? Right space. Okay. And 100. I'll tell you what, let me make myself into a student. So if it doesn't show up as a student, then I know I need to go back as an instructor and fix a problem. So sometimes you can go into, you should be able to find it in quizzes. Let me see. There are the reviews. There's exam one. Okay. You should also, that just gives you the exam. If you go into content and down to learning modules, where are they? Here they are, module one.
How I usually find my work is I go to assignments and I find them from there.
No, exams, what Brightspace calls them quizzes. Exams are not found in assignments. They're found under quizzes. Uh,
Okay.
or you can go into, like we're doing now, go into content, into the module, and then scroll down to the bottom. And here's exam one. What I've tried to do is this useful information for exam one is once you go into lockdown browser, it doesn't let you access any other files. So if you, I would suggest you print this out so you'll have it. And then I've also tried a trick that I just learned of putting this useful information into the first question of the exam. And you'll see it's a link. If you click on that link, then it'll open up in a separate tab and it'll stay there while you're doing the exam. So I'd in the beginning, let's do it both ways. Make a copy of this one and then try the other way. And that way you'll have access to useful information. And if it works, then I can do away with the extra uh, copy that I've been using for 7 or 8 years now.
I don't know why, but I still can't find it. Maybe I'm looking under the wrong thing.
Let's see. Are you going into module one?
Um,
Module one. Should be able to find it on the left-hand side. Scroll down. There's module one. All right, click on module 1 and then scroll to the bottom. And there should be an exam 1, chapters 1 through 3.
I don't see anything that says module one.
Really?
Maybe it's just me, I don't know.
Are you are you in the right course?
Introduction to chemistry, yeah.
Yeah.
Content.
Um, okay, let's go back to the course home and see if this looks familiar. Is that what it looks like when you hit your landing page there?
Yeah.
Okay. So you should be able to go to um, actually you should be able to go to quizzes and drop down to the first. When you do it this way, um, the useful information doesn't come up. And then you have to go to the bottom and launch Lockdown Browser. If you don't have Lockdown Browser, it'll tell you that you don't have the most recent version, and then you have to go back and download and install the latest version. No luck?
Mm, no.
There's
The only one I found is some summary chapter one review essay. Is that the one?
summary chapter 1. No, I don't do any essays. There shouldn't be any essay. I wonder if you're in the right course.
I'm pretty sure I am. 100%. I only have one chemistry class, as you know.
Yeah, yeah. Yeah, you should be in this class. Well, let's go to the top, say table of contents. Okay.
Okay, I'm there.
Okay. Does it look like this? Where you have who is your
It
instructor?
does, yeah.
Okay.
100%.
Okay. That's good. Step 1 is good. Then scroll down the left-hand side and click on Start Here Lessons and Resources. Okay.
Okay,
Then scroll down and you should be able to also find Module 1 here.
did find this one, yeah.
Okay. Then we can go down through Module 1 and scroll to the bottom where it says Exam 1. Oh, I may still have a restrictor on it. Um, let's see. No, I thought I disabled that. You should be able to click on that and find Exam 1 there. If you can't, then I'll have to go out as
Okay.
instructor.
Yeah, I found it. I found it, yeah.
Okay, good, good. All right.
Sorry about that. It was my
That's
mistake.
okay. I'm going to leave this discussion in the video. So if other students come in here and see this, they may have the same question. All right. So let me back out of that one. And let's see, I'm going to go back over here and stop that share and reshare the PowerPoints. There we go. That's where we left off. Okay. Let's get that out of the way. All right. So this is how we read and write chemistry, is using the element symbols. And here's a copy of you've probably seen this before. This is a copy of the periodic table I gave you with the symbols that I want you to memorize in red boxes. Sometimes it's hard to tell which is which. These right here are not outlined. Right here. These guys are not outlined, so you can see where the red boxes are not going. The only ones of the lanthanide and actinide series is uranium and plutonium for historical reasons. So the rest of them I do want you to memorize. And that's why I gave it to you guys at the very beginning of the course so that you could ease your way into it, because memorizing this many symbols takes time. All right. Okay, so let's talk about we've identified elements already, the simplest indivisible form of a substance, chemically indivisible. And elements are made up of atoms, right? So you can have an element with billions and billions of atoms, but there are no other atoms but that particular one. And abundance, if we go by mass percent, and that historically, that's the way elements were identified and characterized by their masses. Up until the um, late 19th century, that's all scientists, chemists had to go on, was the mass. They didn't understand yet that chemistry happens on the atomic level with individual atoms, not with individual masses. But if we look at mass percent, we find that oxygen is the most abundant, excuse me, in the Earth's crust, in the oceans, in the atmosphere. And that makes sense. I mean, the atmosphere has 21% by mass of oxygen. Actually, that's close to mass, 21%. And there's that percent again. You got to know what we're talking about when we say percent. This could be atom percent. That is, 21% of the atoms are oxygen. But since the other 79% is nitrogen, and oxygen and nitrogen are next door neighbors, they're pretty close. So this, if this is atom percent, it won't vary much from mass percent. So there's where a lot of the oxygen is located. And then, of course, the oceans, right? The oceans are predominantly that, right? Since hydrogen doesn't have much mass, most of the oceans is oxygen. And then in the crust of the Earth, most of the elements, metals and nonmetals alike, are oxides. Right? They'll have some metal or nonmetal and then oxygen attached to them. So that's why oxygen is the most abundant element on Earth. Now, we're not going down below the crust. Then things get a little more complicated. And oxygen is less common. The next most common element is silicon. So that's oxygen. Silicon is predominantly a crust element. We don't find much silicon in the air, except maybe fine dust particles. Don't find much in the oceans. But there's a lot of silicon in the Earth's crust. Silicon dioxide, various silicates, where silicon is only a part of the structure, accounts for its abundance. Then aluminum is the next most common element, iron, calcium, sodium, potassium, all of those alkaline metals and alkaline earths. And then hydrogen has a very low abundance, simply because as a mass percent, it doesn't have much mass. There might be a lot of those hydrogen atoms around, and obviously there are because of the oceans. But on a mass basis, hydrogen is not that abundant. And then we have some lesser abundances over here. All right. When we say element, we could be talking about a single atom, or we could be talking about a collection of atoms. It could be a molecular element also. The diatomic elements, for instance, hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, iodine. Right? Those are all the diatomic elements. They're still elements. They just tend to occur attached to their neighbors in pairs. We could be talking about ions also, right? The metals that occur in our body are predominantly ions, sodium ions, chloride ions, potassium ions, uh, some calcium ions, maybe in the blood plasma. Calcium in your bones, of course, is in compounds. All right. So the symbols you should have already surmised, and I think I mentioned it before. The symbols, and your textbook will give you a good rundown also of where these symbols came from. Um, when the elements, when modern science was in its infancy, there was a push to identify the elements once we knew what they were, and many of them came out of the Dark Ages, the Middle Ages, from alchemy. So they had dibs on the symbols that were used. The alchemists, though, had some strange set of symbols, and I think I've got it. I think I put it in. Did I put it in here? Nope, I didn't. Sorry. I need to put that in there. I've got a slide that I've put in some of my lectures that show the symbols, the alchemist symbols for the elements. And there were some really strange ones. You think it's hard to memorize the ones that the way that we have them now? Just try to memorize the alchemist symbols. Fortunately, cooler heads prevailed, and the proposal from Berzelius was accepted. A Swedish chemist, Berzelius, proposed that the symbols simply have one or two letters to identify the element. And there were some that, like I said, had dibs. They were early identified as elements. So they got the one letter symbols like oxygen and nitrogen and hydrogen and phosphorus and sulfur, so forth. But if we got to the point where we needed to go, when we needed to use one of those letters again, then we just tacked on a second letter. And the first letter is always capital. For instance, that would be nitrogen. But we wanted to identify neon. So we put another letter there. That's neon. In this case, in the cases where you have two letters, the first one's always capital, the second one's always small. If you put anything else, it's wrong. You can't do this. You can't do this. You can't do this. None of those are neon. Now, a great many of the element symbols are derived from, can be associated with English names or the names that we use for the elements. But some of them have their letters derived from the Latin names. In this case, oxygen and krypton are obvious, derived from those names. O for oxygen, Kr for krypton. Examples are gold. Gold is Au. It's not Gu or Go. Au for aurum, which is Latin for gold. Lead is Pb, which is an abbreviation for the symbol for plumbum, which in Latin means heavy. So that makes a lot of sense. Others are iron, like ferrum, right? Let's see. Ah, right. That's copper, cuprum. We don't say CO because that one's already taken by cobalt. And there are some others. And most chemistry textbooks have both types of ways of presenting the elements and the names and their symbols. This is an alphabetical list of not all of the elements, but the most common ones. Periodic table, of course, lays them out in a different fashion. Now, when you're building your periodic table, if you're going to do the extra credit, then you'll need this type of list, which associates the elements with the names. And this is probably what you used to construct your flashcards to memorize the symbols. Because many periodic tables don't have the names, they just have the symbols. And the periodic table that I'll give you to be used on the exam doesn't have the names. It only has the symbols. So you have to know what the symbols mean. But this table here associates symbols with names. And you can see the ones that are Latin derived are in parentheses. Right? I think that's misspelled. Stibium, it should be stilbium. Cuprum, aurum, ferrum, plumbum, we did those already. Mercury's kind of weird. Hydroargyrum. I won't go into that history yet. Kalium for potassium, just a K. Argentum, Ag for silver. Na for sodium, natrum. Wolfram's an interesting one for tungsten. It's just a W. Okay. Now let's go down into the microscopic region. John Dalton was often credited as being the first experimental scientist or experimental chemist. But he had his hands and fingers in a number of pies. But as is often the case, scientists will propose these laws to describe the behavior of natural systems. And there's no attempt or any attempts that are that they do try fail. So the laws stand as just descriptive expressions of what's happening. And we don't know why. So the first one we come across is the law of conservation of mass. This was by Antoine Lavoisier, who was a French nobleman. He had lots of money, and he got more because he bought a contract from the King Louis the 16th, I think, to collect taxes for them. And that's the way it was done in those days. Somebody would buy a contract from the king, and they would be allowed to collect taxes from a certain area, a certain group of people. And then the king would assess a tax on that region, and the tax collector would pay that, and anything left over was his. So it could be a lucrative business. And in those days, tax collectors were just as reviled as they are now. But Lavoisier's work established the fact that during a chemical reaction, when one or more substances, it's changed into one or more other substances with different identities. Once we've identified that chemical reaction, Lavoisier said that the total mass of all the reactants is equal to the total mass of all the products. That's the law of conservation of mass, which means that matter is neither created nor destroyed. Okay. So, by the way, Lavoisier, he didn't last much longer than that theory. Let's see, when was it? 1773. Okay, the American Revolution was 1776. It was over by 83, I think. And then shortly thereafter followed the French Revolution. And the French Revolution took on a completely different character than the American Revolution. The French Revolution, once power changed hands from the king to the whatever they called the parliament there. In America, once we gained our independence, we were more interested in individual liberty and liberal thinking in that way. But in France, they were more interested in taking revenge on their enemies and top down. See, they didn't give up the top down governance that they had before. The royal governance was one king governed the whole place. The revolutionaries, they had a committee of just a few people with all the power, and they said what happened. And lots of times they said that off with your head. And that's what happened to Lavoisier, probably because he was a tax collector. So they did that to him. They did that to King Louis the 16th and his wife, Antoinette. So shortly thereafter, Joseph Proust was an Englishman, and he proposed the law of constant proportions, or the law of definite proportions. What that says is that when you identify a compound, and we know it's made up of two or more elements, that's a compound, you identify that compound, purify it, and then determine what its composition is. What percent by mass is this element? What percent by mass is this element? And so forth. What Proust is saying is that it doesn't matter where that compound comes from, whether it's from a chemical reaction or whether you just purify it from a naturally occurring source. It will always have, from any source, will always have the exact same composition by mass of the elements. That's definite proportions. We use water as an example. 8 grams of oxygen is ratioed to 1 gram of hydrogen, always. Whether you purify water from the seawater or whether you react hydrogen and oxygen and collect the moisture, it's going to be exactly the same ratio of oxygen to hydrogen. Same for carbon dioxide. Any compound will do to demonstrate this theory, this law. Then comes John Dalton. And John Dalton took Proust's theory one step further. And this is where students sometimes get confused. The law of definite proportions simply says that the compound has a fixed composition of elements. The law of multiple proportions compares binary compounds that have the potential, that have different ratios of the elements. And I use nitrogen and oxygen, right? NO2, NO3, good examples. Now we know this is the ratio of atoms to atoms now. Dalton didn't know that yet. What he said was that if you hold the mass of the one element constant and ratio, using Proust's law, ratio the second element to the first one, then that ratio number will be over here, be some value x. Right? That ratio will be some x percent of oxygen, okay, in that compound. Then if you do the same thing for this one ratio to that one will be 2x, and this one will be 3x. He said the ratios of those second elements is fixed by a whole number multiple. This is multiple proportions, the law of multiple proportions. All right. Okay, so we have these theories, and there's several others, but these are the major theories. So Dalton's contribution to chemistry and the use of these laws is his atomic theory. Every once in a while, see, most scientists, most chemists, most physicists, they spend their whole careers tearing stuff apart to see what it's made of and the mechanism, small parts, to how they fit together and all that, and how the system works. Every once in a while, you get a brilliant mind come along and take all those different pieces that other scientists have broken apart, pulls them together into a coherent story, a theory, if you will, of why things work the way they work. Dalton was one of those persons. He proposed this atomic theory, and his jumping off point was ancient Greece. The atomic theory, the theory of atoms, that everything was composed of an elementary particle, very small, indivisible particle, was from the ancient Greeks. The problem with the theory in ancient Greece was they thought everything was made out of the same atom. So they had a difficult time explaining why water is liquid and the earth is solid if they're made out of the same stuff. So what Dalton did was he took that concept of the atom and modified it to solve the problem. Okay, so we have some various postulates that are characteristic of the atomic theory. The first one is natural materials are mixtures of pure substances. Now, a pure substance, I think we've talked about that before. A pure substance, I hope we have, is any substance that cannot be reduced further by physical means. Right? It could be a compound. It could be an element. So we don't reduce it by chemical means because that would break the compound apart. A pure substance simply is the pure element, the only that element, or only that compound. It's like pure gold or pure water. And most substances in the most materials that we encounter in nature are mixtures of those pure substances. Excuse me. These are postulates that he's drawn. Dalton is drawing from historical laws. So a given compound always contains the same proportion by mass of elements. That's the definite proportions. So with those laws that we've talked about, and with those postulates that we have seen there, actually they're not postulates, they're observations. Now Dalton in the early 19th century is going to propose this theory, and these are his postulates for the theory. Elements are made up of tiny particles called atoms. All right. Now that's no big that's no revelation. That came from the ancient Greeks. What Dalton says is that all atoms of a given element are identical. But atoms from one element are different than the atoms of another element. That's how he got around the problem that the Greeks faced. See, the ancient Greeks were not noted for being experimental scientists. They were not experimental at all. They did everything up here. In fact, only some of them wrote stuff down. Schoolboys, who were tutored by some master, they did all their lessons, they were writing in the dirt. I would use sticks and they would write their equations, draw their geometry, whatever they did was, and nothing was on paper. Nothing was on stone. Nothing was even permanent. They were all up here. But experimental science requires that when you propose something like this, you got to prove it, right? That means experimentation. So all atoms of a given element are identical, but the atoms of a given element are different from those of any other element. So here are examples of compounds. Atoms of one element can combine with atoms of other elements to form compounds. And the compound has the same relative numbers and types of elements. Now we're accounting for the definite proportions and multiple proportions at the same time. Okay, atoms are indivisible in all chemical processes. Chemical changes will never create or destroy an atom. All right. They simply change places. They swap partners in the chemical reaction, and the substance that they produce has a different identity. Okay, which of the following statements regarding Dalton's atomic theory are still believed to be true? Well, elements are made of tiny particles called atoms. Oh, yeah, that's true. All atoms of a given element are identical. Nope, not anymore. We're going to talk about that in a minute. They're called isotopes. Now, chemically, they are so similar, they're essentially the same, but they're not identical. And in order to prove that, we have to go subatomic. A given compound always has the same relative numbers and types of atoms. Yes, always. Atoms are indestructible. No. They can be broken apart. They can be changed into other atoms. Right? So that's the same, and that's the same. So when we chemical formulas are written to describe the numbers and the elements, the numbers of the elements in that association. It has to be atoms of two or more elements. So H2 or dihydrogen is not a compound because there's only one element. It is a diatomic element. Compounds have to have two or more different elements. The chemical formulas tell us the types of atoms, the elements, and the numbers of each. So I think I've got a slide coming up, but I think it's more important that I do this now. When you have a symbol for an element, like that, I'm going to use X because there are no elements with just X. There are 4 positions around that symbol that are reserved for specific information. This one is the number of atoms. Right? That's what it means. If there's a 3 in that position next to the oxygen, that means there are 3 oxygen atoms in this compound. This one is reserved for charge, right? So many positive, 1, 2, 3 positive, 1, 2, 3 negatives. Or if there's nothing there, then it's neutral. Over here, this position is the number of protons. And we're going to have to define what protons are. Let's see. This one is the mass number. And that's equal to the number of protons plus the number of neutrons. Okay, so those locations are reserved for information. I'll have to fill you in on this side in just a minute. But when we write the compound, if there's only one atom in the compound, we don't put a subscript of 1. That would be redundant, right? And there are 2 rules that we follow when we're identifying a compound, naming a compound, and that'll come up again. Is number 1 is the name must be unambiguous. That is, this formula, when we name that formula, the name cannot mean anything else but that. It's unambiguous and non-redundant. In chemistry, we don't like to chew our cabbage twice. All right? If there's a symbol there, that means there's one atom. And we don't have to put a subscript of 1. All right. How about this one as an exercise? The pesticide known as DDT paralyzes insects by binding their nerve cells, leading to uncontrolled firing of the nerves. Before most uses of DDT were banned in the US, many insects had developed a resistance to it. It was still very effective, even though we had some resistance. And it would, that's the way that malaria, yellow fever, and many other insect-borne diseases were wiped out in the Western Hemisphere, was using DDT. So if we want to write the formula, there are 14 carbon atoms. There's your carbon, and there's 14 of them. Hydrogen atoms, we have 9 of them. Okay? And chlorine atoms, we have 5. Okay? That is known as the molecular formula. The molecular formula for that compound. Okay, now we're going to go subatomic. And you may be wondering, why do we want to go subatomic? Because we know that these atoms are unique in their identity, the way they behave with one another. We just don't know why they are that way. Not yet. So once we discovered that atoms are made up of subatomic particles, and they have these particles in common, and how many of them and how they're arranged in the atom determines the chemical behavior of that element, that atom. Then it becomes clearer. And the subatomic investigations that occurred over 150 years or so allow us to make predictions about their behavior. So there are a number of scientists, and we're not going to go into all of them, but we're going to hit the high points. So the first one we'll talk about is J.J. Thomson. He was an Englishman working at the turn of the 20th century. And he was working, it was very popular. Electricity was very popular in those days. In fact, it was a party favor. They knew how to generate electricity from stacking zinc and copper discs together with vinegar-soaked paper between them, and you could make a battery, right? A voltaic cell. Or you could generate static electricity with a device that that picked up on this big sphere, and then all the party guests would be holding hands in a line, and then one of them at the end with a device would touch that globe, and the static charge would travel down the line, and everybody would jump, and they'd have a big laugh and drink some more wine. But one other device that was used by scientists, those who were investigating the nature of the atom, was the cathode ray tube. And it was a device that used batteries at this time to send something called a ray. They didn't know what it was made of yet, from one electrode to the other inside an evacuated tube. And J.J. Thomson postulated that this beam was composed of negatively charged particles. They had mass, they had kinetic energy because they were moving really fast. And he said, and they knew the difference between positive and electric charges, so he used magnetic fields and electric fields to deduce that these particles were negatively charged. And they were coming from the atoms, and it didn't matter what the material was, the source inside that cathode tube, it made the same ray, right? The same element. So this is a common subatomic particle for all elements. And this is a mock-up, a reconstruction of the cathode ray tube that Thomson used. They they also constructed them with devices inside the tube, right? To either a solid thing to cast a shadow, or a little pinwheel, which made it spin, which showed that they had mass. I think I've got a video coming up too.
Cathode rays are produced in a discharge tube. A vacuum pump is used to evacuate the discharge tube. The cathode of the tube is connected to the negative terminal of the battery, and the anode of the tube is connected to the positive terminal of the battery. It was observed that, at normal pressure, the gas did not allow the current to pass through it. However, when the pressure of the tube was reduced to 0.001 mm Hg, and a high potential difference between 10 kV and 20 kV was applied, at the end of the tube, a glow was seen on the walls of glass tube. The rays emitted by the cathode travel towards anode. The attraction of rays towards anode reveals that the rays carry negative charge. Properties of cathode rays are: 1. When any object is placed in the path of the cathode rays, these rays cast shadows. This shows that cathode rays travel in straight line. 2. When a wheel was placed in the path of cathode rays, the wheel rotates. This shows that rays consist of some particle and some kinetic energy. 3. In the presence of an electric field, the rays are deflected towards the positive plate. This confirms that cathode rays consist of negatively charged particles. 4. In the presence of a magnetic field, the rays are deflected. This shows that the cathode rays are affected by the magnetic field.
Okay, let me back up one. Get the date. Back up two. So let's say about 1900. And his claim to fame was the electron. Did I spell his name right? Nope, doesn't have a P in it. Thompson. There we go. Okay, so now we knew that the atom was not just a jelly-filled bag. That's what they thought with John Dalton's proposal. Okay, so the atom was known to be neutral. So that means if there are electric particles in there, the electrons, then there must be a balancing charge of positive in the atom. Now, we don't know if it was J.J. Thomson that proposed this model. It could have been Lord Kelvin, William Thomson. The plum pudding model was proposed. All right. To account for the positive charge. But they didn't know that it was a particle yet. They just said the matrix within which the electron resides has a positive charge that exactly balances the electrons, right? And they used the English dessert, the plum pudding, because pieces of plum represented the electrons and the rest of the pudding represented the positively charged parts of the atom. Left out one thing. J.J. Thomson was able to determine the ratio of charge to mass. Charge to mass ratio. But he was not able to deduce the mass of the electron. That's as far as he got. So along comes Robert Millikan, who was an American physicist, chemist, and he performed experiments. In 1909 was when the work was published, I believe, on the electron using a device that he built himself and conducted what's known as the famous oil drop experiment. And he was working on electrons, but he determined the mass of the electron using his experiment. I think I've got a video for this one too, so I'm not going to bore you with details. First, he determined the magnitude of the charge on a single electron, and then he used the charge mass ratio from Thomson's work to determine the mass of the electron. Once he had that unit charge for the electron, then he could use Thomson's numbers to determine the mass of the electron. Turns out to be very, very light, 10 to the minus 31 kilograms. And he received a Nobel Prize in 1923 for his work on the electron. Well, actually, it was a dual purpose Nobel Prize. One was for his work on the electron, and the other was for experimentally verifying Albert Einstein's photoelectric effect. Okay, so this video is going to describe that experiment. I hope.
In a series of experiments carried out between 1908 and 1917, R.A. Millikan succeeded in measuring the charge of the electron with great precision. In his experiment, a fine mist of oil was sprayed into the upper chamber with an atomizer. Some of the tiny oil droplets fell through the hole in the upper floor, and Millikan was able to determine the mass of an oil drop from its terminal velocity. Next, Millikan used an X-ray source to ionize gas molecules in the chamber. Electrons from this ionization process adhered to the oil droplets. The oil droplets now carry a negative charge. The negatively charged oil droplets can be halted by adjusting the voltage across the two plates. As the voltage across the plates is increased, the velocity of the oil drops slows. As the voltage is increased further, some drops will begin to move upward toward the positive plate. If the voltage is set just right, an oil drop can be suspended. When an oil drop is suspended, its weight, mass times acceleration due to gravity, is exactly counterbalanced by the electric force applied. The electric force applied equals the applied electric field, E, times the charge on the drop, Q. Since the mass of the oil drop, the acceleration due to gravity, and the applied electric field are known, Millikan could solve for Q, which is the charge on the drop. Millikan found that droplets had different charges, but each was a whole number multiple of a smaller charge, equal to negative 1.60 times 10 to the negative 19th coulombs. Millikan concluded that this was the fundamental unit of charge, the charge of an electron. From the charge of an electron and the charge-to-mass ratio of an electron determined by Thomson using a cathode ray tube, Millikan was able to calculate the mass of an electron. The mass of an electron, 9.10 times 10 to the negative 28th grams, is an exceedingly small mass.
Okay. So we'll move to the next. Let's see. There we go. Okay. So next in line was Ernest Rutherford. Yeah, Ernest Rutherford. In 1911. So it's like a snowball. Things are starting to move fast. Ernest Rutherford took issue with the plum pudding model. He believed, and I'm not sure how he came up with this idea, but he believed that the atom was not diffuse positive charges within which electrons were scattered. He simply believed that the atom was made of a very dense, concentrated positive nucleus, and the electrons resided out in this empty space. So he proposed the proton as a particle, a positively charged particle that would balance the charge exactly of the electrons. So it'd be the same number of protons. Well, in order to demonstrate or prove that his model was a better one than the plum pudding model, he devised what's commonly called the gold foil experiment. All right. So it looks something like this. He proposed that if Thomson's model was correct, and you had this device with detectors all around the gold foil, then if Thomson's model was correct, then these particles that were fired at the gold foil, and had to be very thin. He knew that if it was more than just a 4 or 5 atoms thick, then it would completely stop the beam. And the beam was composed of alpha particles, right? Radiation work at this time had identified basically 3 types of radiation. The alpha particle, let's see, the beta particle, and the gamma particle. See, that's not a good one. Gamma particle. The alpha particle was essentially a helium nucleus, we know now, but it had a 2+ charge. Very heavy. We knew that. It was a very heavy particle. Betas are essentially electrons that originate in the nucleus. And gamma particles they're just light energy. They got no mass. So he used a radiation source that generated alpha particles. And he used gold foil for 2 reasons. One is the gold atom is very large, right? It had a huge nucleus. But gold could also be hammered very, very thin. So in this experiment, these alpha particles were fired at the gold foil, and he reasoned that if Thomson's model were correct, that everything was so diffuse that the beam would travel straight through and not be deflected at all. But if his model were correct, then there would be some deflection, some slight deflections, or some would almost bounce straight back if there were a very heavy nucleus in his atom. So he and his students, he had some research assistants and graduate students that actually performed the experiments for him. But they discovered that his model was correct. Most alpha particles did pass through the gold foil. That's because most of the atom is empty space with very light electrons. So there was very little deflection. Some were scattered, some were bounced straight back. So this is an animation showing what to expect from that experiment. Another animation. Right, straight through would be like that. If they struck the nucleus or got close to it, they would be deflected. Okay, enough of that. And then this is an animation without narration. What you're seeing here is this lead line source of alpha particles, and they're going to come out of there, not in a straight line. It shows straight line, but really they kind of spread out. And these are known as collimators. They're two screens that have holes in them. The holes are perfectly aligned, and only those that are going straight, the particles going straight, will pass through both of them into the detector, strike the gold foil, and produce a pattern on the detectors that surround the target. Right? Okay. So now we have an idea from these, essentially these Dalton's theory that proposed atoms, Thomson that gave us the electron as a particle, but the plum pudding model, which essentially failed. We left out Millikan, who confirmed that the electron has mass and determined what that mass was. And then Rutherford proposed the nuclear model that laid the plum pudding model to rest. In other words, it threw it in the trash can. And then subsequent experiments, in fact, one of Rutherford's research associates, he was a graduate student and then he stayed on with Rutherford as a research associate, was, let's see, Chadwick. I don't remember his first name. Chadwick was given the task of finding out where the rest of the mass was in the atom, because what Rutherford's team had discovered was that the proton, and they determined the mass of the proton, did not account for all the mass of the atom, except in rare occasions like hydrogen. But the rest of them, there was some unaccounted for mass of the atom. So he set the Chadwick on that task, and Chadwick found the neutron at some time after. Now, Rutherford got a Nobel Prize for his work. Chadwick got a Nobel Prize for his work. Now that we had identified all of the particles, subatomic particles that make up the atom. So our atom has neutrons and protons in the nucleus and electrons out here, outside the nucleus. That's as far as we've gotten so far. The modern concept of the atom, I throw this in here because we're not going to go into that much detail. Electrons can behave as waves. They have both particle nature and wave nature, like light. Light has particle nature and wave nature. And where they're positioned around the atom and their energy levels around the atom determine its chemical behavior. I mean, it's only logical. When two atoms approach each other, if they're going to react, what do they see first? Now we know they see electrons first. So the interactions of those electrons, those waves, those regions that they occupy, that determines the chemistry. All right, let's see. We leave anybody out? Well, we haven't gotten. Okay, that last statement. There were dozens of scientists working on this problem. And we only mentioned a couple of the main ones. Niels Bohr took the nuclear model. Let's see. Yeah. Niels Bohr took the nuclear model and proposed energy levels for electrons around the atom. And he was using the planetary model, like the planets of the solar system around the sun. The sun would be the nucleus and the planets would be electrons. He was using that model. And he said that these various energy levels were occupied by electrons, and they never occurred in the regions between those orbitals. Right? So the electron could be here, it could be here, it could be here, or it could be here, but it couldn't be in between. That's known as quantized energy. Only specific quantities of energy would explain where these electrons were. And he came up with a formula for the hydrogen atom. His theory only worked on the hydrogen atom, because once you start getting lots more of electrons in here, you get interactions between those similar charges, and then his theory falls apart. But it was a start. When Erwin Schrödinger, who was a physicist and a mathematician, and he proposed wave equations, a series of wave equations, a set of wave equations that described the nature of the electron, and took it the next step from Bohr's model. And eventually this led to quantum mechanics, with the input from a host of other scientists. Okay, so now we have the nuclear model, 1932, Chadwick, here we go. So it took him a few years to find the neutron. Now, the electron is extremely small, very light. The proton and the neutron are almost the same mass. Neutrons just slightly heavier. But if this is a unit mass, the proton will be about 830 times that mass. So there's a huge difference between the two. All right, electrons are found outside the nucleus, protons and neutrons inside the nucleus. They knew the neutron had to be neutral because the number of protons that were found in the nucleus just matched the electron number. So whatever the mass was due to, it had to be neutral. So Chadwick's work started with neutrality. This nucleus is very dense. Now that brings up the question, as you add more protons to the nucleus, how do you keep them in there together, right? Because they're all positive charges, aren't they trying to push each other apart? Electrostatic repulsion. Well, yes, except for this special force called the strong nuclear force. Once you get them close enough, then they bond together. And they bond together not in and of themselves. That's one of the purposes of the neutron. The neutron is there to mediate the adhesion of protons in that densely packed nucleus. Well, I was close, 1836. All right, so now we know that what the atoms are composed of. They're subatomic particles. But why do they have different chemical properties? Why do these elements have different chemical properties? It arises from its electrons. How many they have and where they're located in these energy levels. Yes, it's true. It is the number of electrons that really determine chemical behavior, but not just the number of certain electrons. There are electrons that we call core electrons. They're the ones that are in here, right? The core electrons. We don't believe that they significantly participate in chemical reactions. It's the ones that are in the outer shells, the valence electrons, that determine the chemistry. And with that thought in mind, we see similar chemical behavior in the periodic table where we have groups. Right? The first group, the alkali metals, the second, the alkaline earths. Those groups, each group has characteristic behaviors. They're not exact, but they're similar in that group. And the reason they're similar is they have, in that group, each element has the same number of valence electrons. Now for the concept of isotopes. Now that we know what the atom is composed of, the subatomic particles, we know that the number of protons determines the element, right? That Z number here. If you know the number Z, the number of protons, that determines the element. Or if you know the element, you use the periodic table, you can find the number of protons. If you change the number of protons, you've changed the element. Now the neutrons is a different story, right? If you have two atoms of the same element with the same number of protons, but they have different numbers of neutrons in each one, so one of them's heavier than the other. You have the same element, but you have different isotopes. And those isotopes have a different mass for each of their atoms. If they have the same number of neutrons, then they'll have the same mass. And the mixture is just, it could be anything, right? So we have whole groups of chemists who do nothing but determine what is the ratio What is the abundance, the natural abundance of each of the isotopes of the elements? So here's an example where you have 11 protons in the sodium, both of them 11, right? But this one has a mass number of 23. So how many neutrons is that? 23 minus 11 is 12 neutrons. But sodium 24, subtract 11 from that, it has 13 neutrons. So it's heavier by 1 neutron. Okay. I described this to you earlier. So here's an example of an isotope of carbon. You've heard of carbon-14 dating. This is radioactive. This will decay. It will change from carbon to nitrogen ultimately. It's unstable. The nucleus is unstable. So we have the symbol, the C for carbon. We have 6, the Z number. The atomic number is the number of protons. We have the mass number of 14, which means there are 8 neutrons, compared to the more abundant carbon-12, which has the same symbol, the same number of protons, but only 6 neutrons. Now, carbon-12 is stable. It does not change. It does not undergo radioactive decay. But these are 2 different isotopes of the same element. So let's see if we can solve this problem. Let me see how far along I am. 4-7. Okay. I need to get a move on. A certain isotope X contains 23 protons and 28 neutrons. Right? What's the question? What's the mass number of this isotope? Well, the mass number is 23. 23 protons plus 28 neutrons. Right? So the mass number is 51. That's equal to A. Okay? Then identify the element also. Well, the identity of the element is determined by the atomic number. 23. Go to your periodic table, and the number of protons gets bigger from top to bottom and left to right. So just keep following along until you find 51, and that turns out to be antimony. Right? 23, 51. Oh, excuse me. I was looking at the wrong one. I said, look for 23, and then I look for 51. 23 is vanadium. Yeah, vanadium. 23, 51. There we go. How about the periodic table? How is it built? Well, historically speaking, the periodic table was proposed. It was developed over time by the work of several different scientists. We eventually came to Dmitry Mendeleev, who was a Russian teacher. And he noticed similar characteristics of elements that I mentioned earlier. Their weights were in a sequence. Their physical and chemical properties were similar, so he grouped them together. And in this first publication, the groups are from left to right. So vanadium, niobium, and tantalum are in the same group. Let's see, beryllium, magnesium are in the same group. Later, on his second publication, he rotated them 90 degrees. So this is what he did for his subsequent publications, and this included more elements. It also included gaps. What he noticed was that when he tried to group elements, and the known elements in sequence of weight would have come from this group, and then the next one would have been here in this group, but it didn't have the right characteristics. It was more like this group over here. So he put it in that group and said, there's a blank. One of these days, somebody's going to discover an element to fit that space, and it's going to have these characteristics. It's going to have this mass. It's going to have this chemical behavior, its physical behavior. Sure enough, when those elements were found, Mendeleev was right. That's why Mendeleev gets the lion's share of credit for the periodic table, because he used it to predict as yet undiscovered elements. Okay, so now we got one. This is kind of dated, this periodic table. Notice down here at the bottom, this UUT, UUQ, UUP, those are placeholders. Now we have actual symbols for those elements. And every element has a name and a symbol. Mendeleev also proposed what's called the periodic law. So you'll notice that when you move from left to right, each time you add a proton. So we go 1 here, helium is 2, lithium is 3, beryllium is 4. Now, why did we swing back around? The reason we swing around is if we put lithium out here on the right, then it's out of its group. It needs to be in this group with lithium, sodium, potassium, rubidium, cesium, and francium. So that's what we call a period. You go to the end of the row and then you circle back. And you go down until you get to the noble gases. And they line up. You don't go past the noble gases because that element, number 11, needs to be with lithium. So that's the period. You go through that period, go back. It's the period concept is, I think, is derived from periodic motion, right? Think of periodic motion as a pendulum, right? The pendulum is moving, yes, but it's not going anywhere. It's just going up here, starts here, swings to this side, and comes back to where it started. Periodic motion. It goes through a period, comes back to start again. And that's what we're doing here. We're going row down here, then we swing around and start another row. That's a period. The atomic number was discovered by Henry Moseley. Henry Moseley was an English student, actually, who graduated and then continued working in the same field. He was working on X-ray emissions from metals when they were exposed to high-energy X-rays. And what he found with his spectrometer was, for a certain wavelength, that he could determine this dominant wavelength. He could determine that wavelength simply with his formula, and all he had to do was insert a number, a whole number, 12, 25, 36, whatever that number is, would generate the exact value of the X-ray, the wavelength of the X-ray, or the frequency, I forget which one it is. And that number he called the atomic number. Now, unfortunately, Moseley, this is 1914, World War I had just started. Moseley was a patriot. He joined the British Army, and he died in battle. So that was the end of his work. But this atomic number was eventually associated with the number of protons. So the periodic table is divided into a major division is between metals and nonmetals. Right? And the metals are usually either a red zigzag line or a heavy black zigzag line. And I'll show you where that is in just a minute. It's also divided into groups or families. We used to call them families, now they call them groups. They have similar chemical properties. And periods are the rows. Okay, so here's that heavy black line right here. Watch as it goes down under boron to the left of silicon, then over germanium, between germanium and arsenic, and it's stair-stepped. If you don't stair-step it right, then, of course, when you do the extra credit, you're going to get points taken off for not doing it right. Then we have various names for our groups, right? Alkaline metals, the first group, alkaline earths, the second group. Transition metals, let's see, I don't think we're given names to a lot of these. Noble gases, of course, halogens are fluorine, chlorine, bromine, iodine, astatine. The O group is known as the chalcogens. Starting with oxygen. Then next to it is the nitrogen group, or the pnictogens. I think it's O. And then that's it for the naming. Well, the lanthanides and the actinides are down here. They fit, the lanthanides fit right in here between 57 and 72. And the actinides fit between 89 and 104. The reason they're extracted out, actually two reasons. One is to keep the periodic table from being so wide, right, to cover the whole board. The other reason is the way the atoms are constructed. And we may or may not get into that, but if you know how to read the periodic table, you can extract a lot of information from it, the way it is set up now. So to the right of that black line are metal or nonmetals, to the left are metals. So most of the periodic table is metals. And then adjacent to that dark line, there are elements that in some circumstances, some situations they behave like metals, in some situations they behave like nonmetals. They're called the metalloids. And the ones that are metalloids vary among authors. Typically, silicon, germanium, arsenic, antimony, maybe tellurium, those are definitely metalloids. Sometimes they throw in polonium and astatine. All right. So here we are again. See, notice that the metalloids are different here. Right? Boron is called a metalloid. Silicon, germanium, arsenic, they stop at tellurium. So it just depends on the author. When we number the groups, the International Union of Pure and Applied Chemists now say that you number them sequentially from left to right, 1 through 18. But you will, some periodic tables, you will also see the A's and B's. 1A, 2A, then over here at boron is 3A, 4, 5, 6, 7, 8A. Those indicate the number of valence electrons in those in that group. The B's are transition metals. They're a little squirrelier. And the reason for that is the way the number and the way the electrons are added in. They're a little bit different than the alkaline metals, the alkaline earths, and the other representative elements. These first two columns and these last six are known as representative elements. All right. Most elements are very reactive. That's why we find very few elements, pure elements, in nature. They're usually combined with something else. Noble metals like gold, platinum, and silver can be found as pure elements. Noble gases, right? They typically don't react with anybody. Diatomic elements, I mentioned those, and they're identified in that special periodic table with the blue background. Right? So be aware of those, because if you encounter a problem that reacts nitrogen, gaseous nitrogen with gaseous oxygen at standard temperature and pressure, you better write them as N2 and O2. Otherwise, the equation that you try to construct will never balance. Well, it won't be accurate anyway. Okay, various states of elements. We mentioned gases, liquids, and solids, but there are some that have different structures. Even though they might be a gas or a liquid or a solid, they have different structures, and we call those allotropes. They're just different forms of the element. And examples are carbon, right? Solid carbon can occur as diamond, right? Has a different structure, gives it different physical properties. Graphite has a different structure, atomic structure, and it has a different nature also. I mean, it's radically different than diamond. Buckminster fullerene was the first of the fullerenes. It's often called a buckyball. It's got 60 carbons in a sphere. And then there are nanotubes that are proliferating, different types of nanotubes. These are all allotropes of carbon. So diamond looks like that. Graphite is sheets like that, which accounts for its different behavior. There's your buckyball. There's a nanotube. And they have very interesting physical and chemical properties. Okay, how do we form ions? Ions are formed by the movement of electrons. Remember, the number of protons determines the element, and the balance between the protons and electrons gives us neutral atoms if they're equal in number. But if we add an electron or take away electrons, then we change the balance. We don't touch the protons because they are specific to the element. So in this case, we have magnesium. It has 12 electrons, balancing 12 protons. If we lose 2 electrons, then we get a 2+ charge, because now we only have 10 negatives and 12 positives. That's how ions are formed, and they can either be positive or negative. If they're metals, most often they're positive. If they're non-metals, most often they're negative. Now they have names. Cations. A cation is a positive ion, and an anion is a negative ion. It can have more than one charge. Doesn't have to have a single. Be 2, 3, 4, or 2, 3, 4 negatives. Here we're forming a chloride ion. The chlorine takes up 1 electron and becomes excess 1 negative. Okay. Now, when we're naming a compound, the metal comes first, the non-metal comes second, and we change the ending on the non-metal to IDE. So chlorine would be chloride. So if we had sodium and chlorine, this would be sodium chloride. All right. There are certain groups in the periodic table that have a fixed charge. When they combine with other elements, they typically assume a fixed charge if they're ionic compounds. Now, I'll clarify that later. The alkaline metals all have a +1 charge. That's the first column on the left. The alkaline earths have a 2+ charge. The halogens have a 1- charge. Noble gases don't have a charge, so that you don't have to worry with those. The one that's left out here is the boron group. So boron, aluminum, gallium, indium. I think that's where it stops. Yeah. These are all +3s. Okay. When they're in ionic compounds. Ionic compound means a metal combined with a nonmetal. There are others that have fixed charges. I'll mention them. Let's see, silver. Silver is always a +1. Zinc is always a +2, and cadmium is always a +2. So those are fixed charges. That's important for naming compounds that we're going to get to in just a second. We did, however, leave out, this would be the position for silver would be right here. This would be cadmium, and this would be zinc. Okay, let's say an ion is identified with a 3+ charge. Three plus charge. So the ion has a 3+ charge, okay? And it has 23 electrons. Okay, how many protons does it have to have? It needs in excess of 3 protons, right? So if it's going to balance these 23 electrons and still have 3 left over, we need 26 protons. Right? That would give you 3 extra positives. So this ion, now that we know 26 protons, we can go look it up on the periodic table. And that's iron. So this would be Fe 26, 3+. Now we're not talking about isotopes here, so we don't have to put anything up there. Here we go. How about this one? A certain ion has a 1 positive charge. Okay, what else does it have? 54 electrons and 78 neutrons. Okay, what's the question? That's always the important thing. What is the question? What is the mass number? Well, in order to do the mass number, we need the number of protons. So this means we need 1 extra proton, 55 protons. And we add these two together, we get 132. Oh, no, sorry. 5 and 8 is 13. And then 1 and 12 is, okay. So the mass number should be 133. Oh, it didn't make us find out what it was. 55. It should be cesium. With a +1 charge. All right. Compounds that contain ions. Ions will combine to form compounds, and the force that holds them together is purely electrostatic. Right? We form a cation, a positive charge, and an anion, a negative charge, and they attract because opposites attract. In this example, we're showing sodium and chlorine. Sodium ions are positive because they're metals. Chlorine or chloride is an anion because it's a nonmetal. Characteristics, they typically have very, very high melting points. It takes a lot of heat to melt sodium chloride. They conduct electricity if they're not solid. If we can melt them, then the ions now are free to move and they will conduct electricity. Or if we can dissolve them in a liquid of some kind, like water, now the ions can move and they will conduct electricity. But as a solid, they're insulators. All right. These ionic compounds are electrically neutral. That is, the positive charges balance the negative charges. So magnesium is an alkaline earth. They typically have a 2+ charge. Right? If you combine magnesium with the chloride ions, which have a -1 charge, that means you need 2 chlorines to balance the 1 magnesium. That's why the formula for the compound is Mg1Cl2. All right. So we got another problem to solve here. I think I'm going to run out of time. Yep, I'm running out of time, but I got to finish. So we'll just keep going. A compound contains an unknown ion X, okay, and has a formula XCl2. Ion X contains 20 electrons. Okay, it's telling us that X is an ion. This is an ion, so it's got to be a metal. And it has 20 electrons. So what would the charge have to be on that X in order to balance these? If these are 1- each, that's 2 minuses that have to be balanced by this 1, which is a 2+, correct? And if that's a 2+, it has 22 protons. So 22 protons is titanium. X would be titanium 2+, actually. Titanium 2+. Okay. All right. Oh, another concept. A member of the alkaline earth metals. Most stable ion contains 36 electrons, forms a compound with bromine. The alkaline earths are always 2+ charge and forms a compound with bromine, which means we need 2 of those because this is a -1. What's the correct formula? Well, 36 electrons, excuse me. 36 electrons means we need 38 protons. So X would be strontium. So SrBr2 is the formula. Okay. Oh, all right, we're done. I guess stop the share. I guess chapter 5 is where we're going to get into nomenclature. Okay, so I was panicking too early. So we'll come back on Thursday. We'll cover chapter 5, which will teach us how to name compounds. So you may want to start, if you want to do the extra credit, start on the periodic table, and that will reinforce your knowledge of the symbols. And then after we get chapter 5 and learn how to name compounds, then you can do the 50 ways to name your compound extra credit. And by the way, the combined grades of those 2 projects is equal to a half an exam grade. All right, we're done for today. I think I'm alone now. Let's see, we'll stop this.